Okay, let's now talk about the idea of a microwave circulator. So remember, we had these three desirable properties that we liked to have in a microwave network. We had matched, we had reciprocal, and we had lossless. So hypothetically, let's suppose I give up the requirement of reciprocity. Okay, so I put in some magical anisotropic materials and my microwave network is no longer reciprocal. What happens now? But I still want to impose the condition of being matched and I want it to be lossless. So let's just write down the formalism mathematically, what that entails. Okay, so by being matched, I've imposed that the main diagonal here is all zeros. But I'm not going to be reciprocal. So that means I have S12, S13, and I'll have an S21, S31, S32, and an S23. So the transpose here, these off diagonals don't have to equal each other anymore. We are, however, going to insist on this lossless requirement. Okay, so by the same argument, you get the simple fact, the requirement, like we saw before, S12 magnitude squared plus magnitude S13 squared is equal to 1. And then I'm going to get S21 squared plus magnitude of S23 squared is equal to 1. And then the magnitude of S31 squared plus the magnitude of S32 squared is equal to 1. So this all just falls out of the requirement of being lossless. And those off-diagonal terms still had to satisfy that weird requirement for S31 conjugate, we got here, S32 is equal to 0. And we have S21 conjugate, S23 is equal to 0. And then S12 conjugate, S13 is equal to 0. So to be lossless, all 6 of these equations have to be satisfied simultaneously. But because we gave up on the reciprocity, that means this little S23 is not the same as this S32. They do not have to equal each other. So it turns out, sorry about this smudge, that if we relax the reciprocity, it is now possible to satisfy this system all simultaneously. And there are, in fact, 2 possible solutions here. So let's look at the first solution now. So let's just write this over here. First solution, I'm going to say, I don't know, you get to be 0, S12. And then I'm going to say S23 is equal to 0, and then S31. Oops, sorry, S31. Let all of those be 0. So that satisfies this condition, while the other 3 are not. And this will also allow for the alternative terms. I'm going to get an S13 magnitude squared, or just magnitude, is going to equal the magnitude of S21, which is also going to be equal to the magnitude of S32, and those are all going to equal 1 now because of these expressions over here. Okay, so we've set a bunch of these to 0, which has zeroed out some of these. So you notice if I set S12 to 0, that means I am letting this guy go to 0, but this one is not. So this guy has to be 1, as you can see. Then I'll let S23 be 0, which forced S21 to be 1. And then I let S31 go to 0, but now my S32 is going to equal 1. Okay, so now I can satisfy everything simultaneously. And when you put all that back into the matrix now, so you'll notice this guy goes away, S23, he goes away, and then that goes away. And these all magnitudes have to be 1. So technically you have some sort of e to the j theta here. But I'm going to just ignore that real quick because that's what the book kind of does. Technically what you should have is something like the following. 0, 0, and then e to the j, theta 1, right? Then I'll have like an e to the j theta over here, 0, 0, then I'll have a 0 e to the j theta kind of thing like that. But if I take the magnitude of it all, so just kind of ignore the phase for now, you basically just have a simple matrix with the form 0, 0, 1, 1, 0, 0, and then a 0, 1, 0, like that. That's the new S matrix. So this is called a circulator. And it turns out, if you do the second condition, so instead of these guys being 0, you make their partners all 0. We don't have to write it out. but you just get a simple result where these rows and columns get kind of rearranged a bit. You can have 0, 1, 0, 0, 0, 1, and then 1, 0, 0. So it just kind of flip-flops a few of your non-zero elements. So these are the two possible solutions if I relax the reciprocal requirement, but still impose matched and lossless. So what does that mean? So let's just draw a picture over here. So the way the book kind of draws it is like so. You have port 1, port 2, and port 3. Let's look at case A here, we'll say. All right, I'm going to call that A or 1, I guess I could have called. And then over here, I'm just going to draw another microwave network. Where we'll do this. This is the second case B, or I guess case 2. But again, 1, 2, 3. So what you'll notice is if I have a signal coming in from 1, then it's going to want to come out of 3, say. Or is that right? No, the signal coming out of 1 will be a function of 3. So the way you draw that is if I input a signal here, so that's what this 1 here is representing, it's going to come out over here. And then, excuse me, let's move this over here. And then likewise, if I have a signal coming into here, it's going to come out over here. So that's what we're seeing over this guy. And then, the third color, if I have a signal come into here, it's going to want to come out over here. So you can draw this as a sort of clockwise circle, right? So if it comes in, it comes out, it comes in, and then or in and out. So you see why it's called a circulator, right? I can sort of add this directionality. So power coming in here will come out, but not come out of this one over here. And then if you impose this matrix onto this guy, you see the exact same situation, but it's just going to go in the counterclockwise direction. Okay, so what that means is if I have a signal coming in over here, it's going to want to come out over here. And then a signal coming in here is going to want to come out there. And then a signal coming in over here will want to come out over there. Okay, so that is called a microwave circulator. And it is a matched loss. It is the only mathematically viable solution to a 3-port microwave network, subject to the condition that it is both matched and lossless, but not reciprocal. Okay, so that is the only logically possible outcome you can have, subject to those conditions.